Okay, so we'll start with lesson 28 now. So in lesson 27, we developed the control model of the ALFC loop, which contained the hydraulic transfer function, which amplifies the signal, then the turbine transfer function, okay, for the generator turbine set, and finally the power system transfer function, which relates the load change in the power system with the frequency, and this frequency by means of a constant known as the regulation constant is converted into the governor signal, which eventually opens or closes the gate by means of hydraulic amplifiers. Okay, fine. Okay, so what is the meaning of static response of the ALFC loop? The static response of the ALFC loop means how eventually the governor reaches the desired frequency, which is 50 Hz, right? What is the desired frequency for the power system? Okay, so how accurately the ALFC loop maintains a constant frequency of 50 Hz, that is the static response. Okay, now how it has obtained that is not, that is part of dynamic response, but we are not concerned about that. We are concerned about the eventual result, which is what is the change in frequency eventually, which should be 0. Delta F should be 0. Now from the block diagram by inspection, if you know how to simplify a control block diagram, so if from there, from various transfer functions, you can eventually find out this expression for delta F, and hence in frequency domain, in S domain, this is the frequency change or the frequency deviation. So this is known as the frequency deviation. Frequency deviation, right? Fine. So this frequency deviation, if you want to know what is in steady state, so limit h tends to 0, delta Fs. So this is the steady state frequency deviation. Okay. Now in this case, we consider a load change of m, and therefore in Laplace domain, you know that it will be m by s. Just like for a unit step function, it is 1 by s. For a load change of m, it will be m by s. So eventually delta F will be equal to, so this is m by s. So the transfer function into m by s, okay, which is minus m plus m divided by d plus 1 by r. Okay, remember it. So in numericals, this equation will be useful. Okay, so we introduce some terms known as the area frequency response characteristics, which is the combination of this load frequency dependency and the regulation constant. Okay, and therefore this static change in frequency eventually is minus m by beta. Okay, so here some example is there where load changes are given. All these examples are in the problem set. I suggest you find time and solve this today itself. Okay, in offline class we would have solved it there in the class. Okay, okay, okay. So that is known as static response. So you are now clear what is static response. Static response means eventually what is the frequency error. Okay, and that can be obtained by means of a step change in load using the transfer function that we have developed in lesson 27. Okay, and you use that equation, limit s tends to 0, delta Fs. Okay, then we need to know what is dynamic response. So as I have said earlier, dynamic response means how this delta F is obtained, how fast the governor is able to reach this change in frequency. So the static response yielded information about the frequency accuracy. Okay, but it did not show the tracking ability and the stability of the loop, and that is given by the dynamic response of the loop. Okay, so for the dynamic response of the loop, you need to get the inverse Laplace transform delta Ft and plot them. Okay, so we simplify by making certain assumptions to make it a linear model rather than a square model, and eventually by converting into time domain, we can get something like this for certain values of Kp, and these are the gains of the power system block. Okay, so by taking some part of that, we can find out this equation, and this is one such example which I have directly taken from the book. If you see here this part is the dynamic response. This is the dynamic response. So how fast it is responding. but every case there is some delta F0, isn't it? It's not desirable. So from your control system knowledge, you know how to reduce steady state errors. So to reduce this steady state error delta F0, which is not at all desirable, it should always be 0, not even this 0.0235 Hz. Okay. So for that we need another loop known as the secondary ALFC loop. So if in the example there is a 2-mark question, why secondary ALFC loop is needed, it is required to make the steady state error 0. To achieve better frequency constancy than by the governor itself, we need a control strategy to achieve stability as isochronous control means simultaneous, separately from the main control. Minimization of integral of frequency. Okay, so this is what is the main thing, minimization of integral of frequency. Stability is always a problem in closed loop control. The tighter the error specifications, the greater the risk. Okay, so isochronous means assures that the synchronous clock runs on time but not without error. Some error is there, but everything is on time, but there is some error. Okay, it guarantees that static frequency error following a step load change will vanish. No control system can, however, eliminate the transient frequency error. The time error of synchronous clocks is proportional to the integral of the frequency error. Okay, this is the reason behind why integral control works. Okay, so eventually we use one integral control. So the previous slide was based the concept of the integral control. So we use one integral control using this equation. Okay, and there we try to make the area control area to be 0. Okay, let me see if you have provided or not. No, I have not provided. So we have to open the last slide. If you see here in a dotted line, I have shown you Ki. Okay, in the previous lesson I have shown you Ki. Okay, so it is better if I show you that again. Okay, this one you see here. So there is this secondary ALFC loop. Okay, so this is the secondary ALFC loop, and that comprises of this integral control, which is ensuring the steady state performance to be 0. Okay, that means there is no error eventually. Okay, so we were here for the secondary control. Okay, so what is the loop response? Similarly, using, so what is the integral control? So this is the integral control. Including the integral control, you need to find out the transfer function of the whole loop, which comes out to be like this. Okay, and if you find the steady state error, you see here without integral control there are some errors, whereas with integral control here, the steady state error has become 0. These are very standard results, and you can always obtain this in any software like MATLAB. Okay, so without integral control, with integral control. Okay, and some problems are there for the regulation constant. You see here the frequency dependency and the regulation constants. So I suggest you go through these problems. Okay, next, the next concept is, what is a power pole? Practically all power systems today are tied together with neighboring areas, and the problem of low frequency control is a joint undertaking. Okay, it's a joint undertaking. Closely associated with the problem of controlling the power flow is the interties. That means how the power systems are connected together. The following are some basic operating principles. Under normal operating conditions, each pool member or the control area should strive to carry his own load except such scheduled portion of the other members' loads as have been contracted. Okay, it had decided to give. Each control area must agree upon adopting regulating and control strategies and equipment that are mutually beneficial under both normal and abnormal conditions. Increase in system size reduces the need for reserve power among the pool members. Okay, because we need not provide reserves, we can simply borrow it from other systems where it is available. A system that operates alone as a single area must provide power to handle anticipated peaks and sudden requirement of due to equipment failures like microgrids, okay, or islanded systems. Okay, but pool members can benefit from a reduced need of reserve capacity. Okay, so going back to this problem, so I would suggest that by the time I take attendance, you solve this problem. Question number 5.2.6. It's a very important problem and very important from exam point of view also.